Welcome to the VMT tutorial on the White Wabash confluence data. This tutorial is a basic tutorial to take you through the steps of importing data into VMT for a single cross-section and processing those transects, that is doing the transect averaging within VMT and plotting the data for visualization. So let's get started. The first thing to do is, if you're going to be running VMT in the MATLAB software environment, you want to go up to, once you open MATLAB, change your path to the VMT directory and type VMT at the command prompt. This will open your VMT graphical user interface window. For those of you that are not running the MATLAB version of VMT, if you're running the compiled version, simply double-click on the executable for the vmt.exe executable, and that should open the GUI window as you see here. You won't get to see the command window, which has some additional output from VMT, but you will see a series of status windows come up telling you about the status of the processing. Okay, so the first thing to do when you're going to load some transects into VMT for a cross-section, the first thing to do is select this ASCII output option. If you've selected the select or save data file, it'll save a MATLAB data file, which then you can go back and load in using this MATLAB file option at a later date, and you don't have to redo all the processing computations within VMT. It simply loads in that saved data file that has both the raw and processed data within it. So we're going to go ahead and select that. Typically I'll leave it off for the first round, but we'll go ahead and leave it selected so it'll save the raw and processed file each time I run the program. I'm going to go ahead and load or leave all the default values as they are in the VMT GUI by default. And this assumes that the user is familiar with the VMT interface to the extent that they've gone through the user guide and the quick reference, and which gives you an idea of what all these buttons do. But basically, you have the graphics export window, the processing panel, the bathymetry export panel, and the plotting panel, both in plan view and cross-section view. And we're going to go through some of these inputs in detail in this tutorial. So I'm going to leave everything the way it is, leave this horizontal grid node spacing set to 1 meter by default, and I'm going to say load data, and I'm going to navigate to my data set. In this case, we're going to be looking at the White Wabash confluence. And once I've selected that directory that contains my ASCII output files, I say OK, and it's going to find all the ASCII output files within that directory and list them here. And I want to select all the ones that I want to process. So if you had multiple cross-sections here, you just select the transects for a particular cross-section that you're interested in. In this case, we just have 4 transects. They're all for the same cross-section, so I say select all, and I say OK. And it's going to give me the status update in this status window. For those of you that are using MATLAB, you'll see some extra output. But it's going to go through and load each one of those data files, do some pre-processing, go through and do the primary processing, that is the transect averaging, and we'll get a series of status updates. Then it's going to go through and do the plotting. We see it's plotting the plan view now, then plotting the cross-section, and finally the plotting is complete. I'm working on dual monitors here, so my plots are coming up on the right-hand screen. I'll move them in here in a second. But I first wanted to show you a couple status windows that come up when you run VMT. The first of these is the grid node spacing window. When you load the ASCII output files, what it'll do is it'll give you some statistics on the spacing of the ensembles along your mean transect line. And so it gives you a median spacing between the ensembles. These are ensembles that have been moved in from the individual ship tracks onto the mean transect line. And so the mean spacing between ensembles is about 27 centimeters. The standard deviation is about 31 centimeters, and it gives you a recommended grid node spacing. So this is something that you want to set your grid node spacing to at least about 60 centimeters or greater. We see that we've got it set to 1 meter, so we're in good shape here. There's also a window, this VMT cross-section characteristics window. This gives you a little bit of of detail on the flow itself. The streamwise direction, flow direction that is normal to your mean cross-section. So it's defined by that mean cross-section and taken to be normal to that. You got the primary flow direction. You can compare this with your mean cross-section, and that gives you an estimate of the flow angle. You can think of having a tag line stretch across your cross-section, and this would be normal to your tag line. This would be your actual flow direction. So the difference is the deviation from the streamwise direction that's shown here is about 2 degrees, and it gives you a horizontal grid node spacing. This is so when you play back the data, you know what the grid node spacing was when you computed the data. That's set to 1, which is what we have in our panel here. So you'll see these windows pop up. They just give you a little more information on your cross-section. You can either leave them up or click OK to remove them. And now I'll move in our various windows that we get. We basically get 3 plot windows. The first of these is Figure 1. Figure 1 gives us our cross-section. I'll go ahead and maximize it. And so what we see here is that the 4 blue lines are transects. So there's the ship tracks for each of the transects that were loaded in the ASCII output files. The black line here that has the plus signs along it, I'll zoom in here in a second, but that's our mean cross-section. So that's a fit to those 4 ship tracks, and so all the data has been moved onto that line. And so if I zoom in here, what we see is we have our 4 ship tracks, the blue lines. We have the green line, which is our mean cross-section, so that's the fit to the 4 ship tracks. The plus symbols here are the grid nodes. These are spaced, as we said, 1 meter apart. And the blue dots are our individual ensembles that have been moved in orthogonally from the individual ship tracks onto this mean cross-section line. So that spacing parameters that I was talking about gives you an estimate of how these are spaced along your line. So ultimately what VMT is doing is mapping these ensembles onto this mean cross-section line and then interpolating at each one of these grid nodes as you have set the spacing on those. So that's Figure 1 in a nutshell. Figure 2 is your plan view plot or plan form plot. This gives you vectors oriented in the direction of flow. They're also color-coded with magnitude. The length and color gives you magnitude. Of course, the orientation gives you direction. And so we got UTM northing and easting on the axis. In this case, we've chosen a depth average velocity. In the VMT window itself, if we go back to that, we can see that by leaving this depth range blank, that's going to give you the depth average velocity over the full measured depth of flow. So that's the measured depth of flow, which doesn't include your side lobe interference and your blanking distance near the surface. However, we can choose to put in a depth range, and we'll do that here in a second. And this will give us our layer average velocity over a certain depth. So, for instance, if I wanted to, I could choose, instead of having depth average velocity for the full measure depth, I could say, well, I just want it between 2 and 3 meters depth. This particular flow, as I'll show you here in a second, is about 7 meters in depth. And I can say replot, and it'll replot just the vectors between 2 and 3 meters. So this is layer average velocity in this case. I'm going to go ahead and delete those and reset it back to our depth average velocity. And so when I hit replot, it'll automatically go back to a full depth average velocity. And I'll bring in our third plot, which is our cross-section plot. It's quite busy right now with the amount of vectors that we're seeing. But what we're seeing is a cross-section, so this is depth and distance along the horizontal axis, starting with your left bank point and moving across the section, looking downstream. We've got our bed profile here, so this is, the white line is our bed profile, the mean of the 4 beams. And we've got a color contour plot. In this case, the color contours relate to the streamwise velocity. We can see here in our VMT window, we had the contour variable as streamwise and the secondary flow vector variable as the transverse. So streamwise is oriented perpendicular to our mean cross section. Transverse is within the plane of the mean cross section. And our title on our figure tells us those two variables that we've chosen to plot. And we've also included the vertical velocity component in the secondary flow vectors. So they have a vertical component included in those transverse, included with the transverse to form those secondary flow vectors. So the next step to actually cleaning up this plot is to identify the proper scaling and vector spacing. We can see in our cross-section plot we have far too many vectors. I'll also go back to our original plot. This is probably too many vectors here as well. It's a little hard to see. So one thing we can do is increase the scale in this plan view plot. So I'm going to say 1.5. I'm going to increase their length a little bit. And instead of plotting every vector, the vector spacing here is set to 1, which means it's going to plot a vector at every grid node. I'm going to plot every other grid node. So that would be vector spacing 2. And I'm going to leave the smoothing window set to 1. So this is going to basically apply a moving average and average every vector with its nearest neighbor. So one node on either side. If I set it to 2, it'd be 2 nodes on either side, and so on. And so I can hit replot, and it's going to replot both my figures for me with the new settings. We've only changed figure 2 here, our plan view plot. We see we got every other vector now plotted, and they're a little bit longer in length. One nice thing that I can do, if I choose to, it doesn't give me much information when you're looking at this. You may not realize that you're looking at a confluence and this is a shear layer. It's obviously an anomaly in your flow. So you can add a background. And if you've already gone through and downloaded a aerial photo or some other kind of georeference imagery in UTM coordinates, that can be loaded in here. So I simply select the aerial photo. This is a geotiff in this case, and say open. It'll ask me if I want to load another one. You can load multiple backgrounds. And I just have the one, so I say no. And it'll bring it into my plot in figure 2 here. And now we see that we are at a confluence. Suddenly the flow distribution makes a little bit more sense. This is the Wabash River here and the White River coming together. We can see that on the day of the photo, the shear layer was shifted a little bit further into the Wabash, but on this particular day that we collected our data, the shear layer was shifted a little bit towards the left bank. So that's the idea behind bringing in some kind of background or digital orthoquad, any kind of georeferenced imagery. If you don't have imagery, you can also choose to plot a shoreline, and it will prompt you for an XY point file of the shoreline points, and you can see the user guide for more information on that. Okay, so we also now want to clean up our contour plot. We see that we've got far too many vectors, so the first thing that we can do is go in and reduce the number of vectors. So I'm going to plot, instead of every horizontal, instead of plotting a vector at every horizontal node, grid node, I'm going to plot every 5th grid node. So I set that to 5. I'm going to keep the vertical vector spacing set to 1. So I'm going to plot every grid node in the vertical, but every 5th in the horizontal. And I'm going to leave everything else the same, and I'm going to say replot. And our plots will replot. Now we can see that we're looking at the confluence. We're looking downstream here. This is the White River, Wabash River. And with the streamwise and secondary or in transverse flow vectors shown, we simply get a zone of convergence here towards the shear layer. We can choose to change the vectors that we plot, or the variables, that is. So we can plot the primary velocity by choosing our contour variable to be primary velocity with the 0 secondary discharge definition. And I'm going to likewise change my secondary flow vectors to be, instead of the transverse component, the secondary flow component with the 0 secondary discharge definition. And I see replot. And we'll see if this computation method for secondary flows yields anything better. In this case, we still see convergence, which tends to make sense. We're at a confluence where we don't have a single primary flow direction, and with the zero secondary discharge definition, the section is rotated such that zero secondary discharge over the entire cross section is zero. So it works best with flows with a primary flow direction, a uniform primary flow direction across the channel. In this case, a Rosofsky method would be more appropriate here, where you're defining a primary flow direction for each individual ensemble or vertical profile of velocity, not for the whole cross section. So I'm going to choose the primary velocity from the Rosofsky downstream component for our contour variable, and I'm going to do the cross stream component as our secondary flow vector. So now we're going to look at the Rosofsky method, and we say replot. And now what we see is that we get a much different flow distribution. The vectors are a little hard to see. They're somewhat small. So I can go back in and I can change our vector scale here, make them a little bit longer. So I'm going to say 0.5 instead of 0.2. This is just an arbitrary vector scale. The larger the number, the longer the vector length. And I'm going to say replot, and it should bring our vectors into a little better view here. There we go. So what we see is we've got a helical flow, convergence at the top, divergence at the bottom, and the two meet at the shear layer. We still have some flow variability here that we can see due to turbulence and other variability within the flow. So we can average some of that out by choosing a horizontal smoothing window. Right now we're doing a smoothing window, which is a moving average, and we're averaging with every point with its nearest neighbor, both in the horizontal and the vertical. So we're taking 1 point on either side. I can choose to take 3 points on either side in the horizontal. I'll leave the vertical set to 1, and so it's just going to average a little bit more data at each point. And I see replot, and you'll see that it'll clean up our plot quite a bit. So now we see that same flow pattern. It's cleaned up a little bit. We've gotten rid of some of that flow variability and really brought out some of the circulation patterns within the flow. Okay. Let me just quickly show you here. If I choose to, I can turn off the vertical component of velocity. We can see that we've got what appears to be a negative bias in our vertical velocity. This occurs sometimes with ADCP data. Randall Deinhardt with USGS has documented this in the past with some of his work, as well as we've had some discussions with TRDI about some of the issues. And if you read our paper on VMT, we discussed that a little bit within the paper. But say you choose to turn those vertical velocity components off, you can do that by deselecting this box, saying replot, and you will end up with basically the same plot without the vertical velocity component within those vectors, but you get the same circulation patterns and so on. Okay, because we had the save data, the MATLAB file button selected here, it's created a MATLAB data file that contains both the raw and the process data in our directory that contains the ASCII output files. So if we go to that directory, this is the white Wabash, we see that we now have a directory labeled VMT process files. This is a directory that contains all the process files from VMT. If we open that, what we see is that we've got this white Wabash data file, and it's appended to the end of the data file name is 017 to 022. So those are the beginning and ending transects for the set of transects that were processed. It automatically appends those to the file name, and it's a .mat file, which sometimes will show up as a Microsoft Office Access file. And so that's what it shows up on my machine here, but it is a MATLAB data file, and that can be loaded in at a later time into VMT, and you skip the processing steps. So there's a couple other options for outputting data from VMT. You can also choose to output a TechPlot data file. It actually outputs two data files in a TechPlot format with a header that's readable by TechPlot. So if we choose that option and go through, I've turned off the cross-section plotting. We're not going to plot them. We're just going to go through the data export here. And I just say load data, as we did before. And I'm going to navigate to my cross-section. That's a white Wabash. And select all. And I say OK. It's going to add one extra step within the processing, and that's the export of that TechPlot data file. Now, depending on the speed of your computer and the size of your data set, you have the ability, it often adds a certain amount of processing time to the VMT runtime. So you'll see this window come up in the status window exporting data to TechPlot. This may stay up for a little while depending on how fast your computer is. But once it's finished, it'll go on to the plotting routines. If there's no plotting selected, it'll tell you everything is complete. And you can check back for your data files. Now, during the TechPlot export subroutine, it's going through and making some changes to the files to reformat missing data and problem data in a format that TechPlot can handle, rather than using the not a number scheme that's available within the MATLAB environment. So it's got to go through and do some reformatting, and that's really what takes some time. There's some loops in there that MATLAB doesn't like. But once it's complete, you see this plotting complete here, and we can go back to our directory that contains the VMT process files, and now we see we have two more files, this TechOut and TechOut cross-section Bathy. So the TechOut file contains all your velocity data from the ADCP, so it's your average cross-sectional data. And then you have your just cross-sectional bathymetry as a separate file. That doesn't include any of the velocity or backscatter data. It's just the 4-beam average data for the cross-section. Okay, and those can be loaded straight into TechPlot and visualized if you so wish. The other option is to do a KMZ file through Google Earth. What this does is creates a cross-sectional bathymetry file. It's a three-dimensional file, basically a slice of your bathymetry for the average cross-section, and it puts it just above the image plane within Google Earth for visualization. And you can load multiple files and view them in 3D and do fly-throughs and that sort of thing. The one catch is that you have to offset your bathymetry up above the image plane so that it's not hidden by the image plane within Google Earth. And so to do this, you take and add a vertical offset to your data. And what I recommend here is using the a value greater than or equal to the maximum depth in your reach, so that no data is hidden behind the image plane. We know that with our cross section we had just over 8 meters in depth for the white Wabash, so I'm going to give it 9 meters here. That'll guarantee that none of my cross section falls below the image plane. And I simply hit load data as before and select all my transects. And so this, like the TechPlot output, it just adds another processing step here, but instead of just creating a KMZ file and storing it, it also will automatically open Google Earth if you have it installed on your machine, and zoom to that cross-section for us. So that should pop up here any second. Now, one thing to note here is that you'll have to have the plotting turned on, because the actual script's called within the plotting routines. So I've turned back on the plotting on plan view and cross-sectional view, and you'll see that once it's done with the plotting, it kicks into the Google Earth export and zooms to our cross-section. And right now, we're looking straight down on our cross-section, so it doesn't look like much, but we can navigate here and pan the camera, and zoom back, and we see that now we're looking at our cross-section in 3 dimensions, looking upstream here. This is the Wabash River and the White River coming in, and we see the nice scour zone that's concurrent with the shear layer. You can rotate this in 3 dimensions here, rotate and get a downstream look. You can imagine where this would be quite nice for multiple cross sections. So you can you do this for each of your cross sections in your study reach. You can load them all in and see how the bathymetry evolves as you move downstream. You can also plot multiple cross sections from different surveys in time and look at how each cross section is evolving in time. Just in the Google Earth environment, you don't have to go in and do a tinning and create a 3-dimensional surface in something like ARC. But that gives you an idea of what you can do with this Google Earth export option. And I'm going to go ahead and close that out. And finally, what I wanted to show you was the option to export multi-beam bathymetry. So again, I'm going to turn off my plotting here. It doesn't really matter because it's not going to do any plotting anyway. Once you select this output multi-beam bathymetry option, the processing stops there and it generates your multi-beam XYZ data file and doesn't kick into the plan view or the cross-sectional plots. But if you select this option, what it's going to do is take and correct your or compute the georeference positions of each of the individual beam depth locations based on the beam angle, your heading, pitch, and roll, and the known location of your ADCP through your differential GPS input. So this is a routine that it applies that was provided to us by TRDI, and it's been implemented in programs such as Dave Mueller's AdMap. But it applies it here given a given beam angle. This is 20 degrees default for TRDI Rio Grande systems that we typically use in the USGS. And you can also provide it a water surface elevation from which it will subtract the measured depths to give you bed elevation. So if we knew that this particular cross section had a 300 meter above sea level water surface elevation at the time of the survey, we can input that here, and it'll give us bed elevations reference to that water surface elevation. We can also choose to output the auxiliary data, and what this does is rather than just giving your XYZ data file, it'll also export additional data that includes a timestamp, heading, pitch, and roll data. And so with these selected, we can go up and select load data just like before, and select the data files that we want to load. You can imagine if you had a full reach survey and 100 transects through your reach, you can select them all and do a batch processing. It's going to do all the corrections and put them into one XYZ data file for you. So it's going to go through and do the preliminary processing of the data and kick into the bathymetry export subroutine, and once it's done with that, it'll tell you bathymetry output is complete. We say OK, and we go back to our VMT process data files, and now we see we have an additional file here, the same prefix for the file name, and then we've got a suffix here, mbxyz. So this is multi-beam XYZ data file. It's a CSV file that I can simply open. Here to give you an idea of what it looks like. This is a fairly simple file. Let me expand the headers here so you can see what we're looking at. We have ensemble number, easting and northing, so UTM coordinates. Your bed elevation. This would be negative. If you didn't give it an elevation, it'd just be negative depths here. Year, month, day, hour, minute, second, heading, pitch, and roll. And so columns D through M here would not be available if you didn't select E through M would not be available if you didn't select the auxiliary data option. And so this particular data file we can take straight into ArcGIS for further processing and visualization. And so I've already loaded the background imagery for this particular site. I can simply go up to Tools, Add XY Data, I can browse to that particular file. And we see we're in the, it automatically put me in there because I was working with this earlier. Here's our white Wabash in my MB XYZ CSV data file. I say add. It doesn't choose the right X and Y field, but I can choose that for it. Easting and northing. And then I select the coordinate system. And this is going to be in UTM coordinates, WGS 84, and this is zone 16 north. So I say add, and I say OK, and one final OK, and then I get a warning message that I need to create a shapefile from this data for further processing. I say OK, and it'll bring my my data into the ArcGIS environment here. And so now I see these are my data points shown in red. I'm going to change the color real quick so when we zoom in we can see them. And so I'll zoom in here and we'll see what our data points look like. These are individual beam depths from the ADCP. So for every ensemble we get 4 of these beam depths. We can open the attribute table here and we see we have that same table of data. Easting, northing, elevation, year, month, day, hour, minute, second, heading, pitch, roll, and so on. So that's one way to bring your data in. From here, you could do you could create a tin, you could crig it, you could however you process your bathymetry data for a particular data set. You can work with it from here. Okay, so. Finally, the last thing I wanted to point out is this graphics export option within VMT. This is a quick option for exporting some of the bathymetry or figure data, and so what you can do is with these cross-sectional plots selected, I'll go ahead and bring one in here from my right screen, and once you have your plots generated. Then you can choose this option. Say this is figure 3 here, so I want to export the cross-section plot, and I want to do it in print form. Presentation form gives you the way it looks on the screen with a black background. If you choose print, it gives you reformats it for a white page, so a white background and so on. And then you simply hit Save Figure. And you see it reformats the figure a little bit, and it asks you for a place to save it. So we're going to go ahead and actually I'll go back here. We'll go ahead and put it with the rest of our files. And I'll just call it Fig 3. And it's going to be, it's automatically formatted in PNG data file. We can change this if a user chooses. This is simply hard-coded in right now, but we could create an EPS file or others, and likely we'll have this user selectable in the future. And we say save, and so it saves our file, and we can go back here and let's see if we can white Wabash. It refreshes. There's our figure 3. And let me move it in from the other screen. So here's our saved figure. This is just in a basic Windows photo viewer, but it's our PNG file with the print option. Again, with the presentation option, it'd be a black background. But that's the basic idea on how to get some of these figures out. You have other options if you're using MATLAB to go up to this file, export setup. You can also do save as, and there's a lot of different ways to get your figures out. But this is a quick and dirty way to do it through VMT. So with that, it concludes this tutorial on the basic data processing within VMT for the White Wabash Confluence. If you have any further questions, please see the user guide for VMT or contact myself, Ryan Jackson, with the USGS, or Dan Parsons with University of Leeds. Thank you.